Great. Welcome to Weekly Science Review 2. This session is being recorded so that people who cannot join real time can watch this and learn from it and get benefited. Vetri Labs, here our vision is to enable implementation of electrochemical technologies at scale. That's the key, at scale. Today's discussion is going to be on electroreduction of CO2, and it's going to be led by Dr. Ayyappan Ilangovan. Ayyappan Ilangovan is a research scientist at Vetri Labs. His research is focusing on electrochemical materials and devices. So during the presentation, we can turn the video off, and during the discussion session, we can turn the video back on. Over to you, Dr. Ayyappan.
Yep. Thank you, Dr. Chok. Right now. I hope everybody can see my screen.
Yes.
Okay. So yeah, today we'll be discussing about rapid product analysis for the electroreduction of carbon dioxide on heterogeneous and homogeneous catalyst using rotating ring detector system. We all know that increasing utilization of fossil fuels is leading to a huge amount of CO2 emissions that eventually results in the increase of our global temperature and leading to an inevitable damage to our ecosystem. So as a result, we want to reduce the greenhouse effect. And the way we can do that is converting CO2 into some kind of usable energy. There are a lot of places in industries where the CO2 is converted into a C1 building block. So CO2 conversion can happen either through a two-step conversion process or in one single-step conversion process. In a two-step conversion process, you initially produce hydrogen through water electrolysis, and then you use that hydrogen to hydrogenate CO2 to produce any alcohols or olefins. And then single-step CO2 conversion, you directly reduce CO2 to produce alcohols and other hydrocarbons. And so single-step conversion is more efficient. In that, we have two sets of whether we can do a photoelectrochemical reduction using a semiconductor catalyst and a stimulated sunlight as a source, as an energy input, or we can use electrochemical reduction of CO2, where we use energy input from renewable sources such as solar or wind, and then convert the CO2 and CO2 emissions from the fossil fuel powered devices and convert back to electrofuels. And then once it's consumed, it gives back CO2, which could be fed back to close the loop. So and then electrochemical reduction of CO2 basically happens on the cathode side, and on the anode side, we either have hydrogen oxidation reaction or oxygen evolution reaction, depending upon the electrolyte we use. And the CO2 electroreduction can be easily tuned by modifying the ambient conditions. So which means that the products that we get is depend upon, and it can have like different possible pathways. Like CO2 you can convert into carbon monoxide or formic acid, or like a higher alcohols such as ethanol, or hydrocarbons such as methane or ethylene. As you look at the reaction here, it involves multiple electron transfer. So you can have either a 2-electron transfer to get to carbon monoxide or a 12-electron transfer to get to ethylene. And it's thermodynamically easy to reduce CO2 to either CO or formic acid compared to other terms of alcohol or hydrocarbons. So now let's focus on what are the different catalytic mechanisms that happens when CO2 is electrochemically reduced. So electrochemical CO2 reduction can either happen through 3 different mechanisms. One is homogeneous catalysis. So in this, the metal complex, like a molecular catalyst, is mixed within your electrolyte solution. So it acts as a redox shuttle between the electrode and CO2. So they do so they accept electrons from the electrode, giving it a more highly reduced state for the catalyst. And then following the reduction, the catalyst then donates the electrons to CO2 in solution and returns to the initial state. So this overall reaction resembles like an indirect electrolysis. Second one is like you can do a surface or mobilization. in which the catalyst is mobilized, like a molecular catalyst is mobilized on the electrode surface. So it involves the advantages of both homogeneous catalysis, and also you can have a selective CO2 reduction to a particular product. The third one is heterogeneous catalysis. Here, the CO2 gets adsorbed on the electrode surface and then goes through a reduction reaction to produce a particular product which gets diffused into the bulk electrolyte. Usually, people generally use a polycrystalline or a monometallic single metal electrodes, but using a high surface area heterogeneous catalyst is an easy way that you can increase the electrochemical surface area of the catalyst, and you can also tune the particular product that you want to produce from electrochemical reduction of CO2. As I mentioned, that an electrocatalyst can be classified into different types. So basically we have monometallic catalyst, and monometallic catalyst can be product selective, and they can be divided into 4 different types. One being selective to hydrogen, because hydrogen evolution is more competitive at the potential where CO2 gets reduced. And then the second one is CO favorable, and the third one is formate favorable. And then we have a unique CU copper-based catalyst, which can produce a mixed range of products starting from CO, formic acid, or methanol or ethanol. And this monometallic catalyst can also be tuned to have like nanostructured or nanoparticles, so you enhance the active sites. And we can also use bimetallic or ion modified metallic catalyst. And there is another set focused on non-metallic catalyst, focused on carbon nanofibers or nitrogen doped carbon, and also molecular catalyst, which has advantages that the transition metal or the ligands can act as an individual catalytic active site. So you can tune down the product that you want from the reduction of CO2. And so the different techniques for product analysis. So there are conventional techniques that can be used to evaluate the product that you get from the electrochemical reduction of CO2. So using gas chromatography, or high performance liquid chromatography, or mass spec, or NMR. The disadvantages with these techniques is irrespective of they have a higher detection limit, but it takes a longer time to get the product. For example, if you want to, for any liquid products, we use HPLC or NMR, you need to have an extended electrolysis time or you need to reduce your volume of the electrolyte that you use for electrochemical reaction, or you need to enlarge the catalyst surface area. So you could reach the detection limit of that particular technique. Whereas for gas-based products, we use online GC system. So the gas products are injected like every 10 minutes in the systems for acceptable separation efficiency between the small molecules. And then there are advanced techniques using in situ X-ray techniques, or IR, or Raman, or scanning electrochemical microscope, or Fourier transform, AC voltammetry. And these in situ techniques has advantages over the conventional techniques, but it still needs a experiment, like a complex experimental design. And also we need to tune down a lot of parameters to efficiently ensure and detect the product that you obtain from the CO2 reduction. And here, this is rotating ring disk electrode. And this is a rapid analysis of your reduction products using a bipotential stat. So you basically have two working electrodes, one being your disk and the other one being your ring. So how an RDE works is, so like when the RDE rotates, the spinning RRDE drags the electrolyte solution from the bulk of the electrolyte to the surface. And due to the centrifugal force, the solution is flinged from the disk surface to the ring, where the reduced products, for example, in CO2, it can form formate, and the formate can get further oxidized to CO2. And by this way, it produces a particular fingerprint electrochemical oxidation peaks that could be used to evaluate which product is formed and what is the concentration and detection limit of that particular product. And as you can see here, in RRDE, you'll have a center disk, which is made of like monometallic, like such as platinum, silver, or like gold. And then you can have also glassy carbon in which you can deposit your catalyst, or when you use a homogeneous catalyst, your catalyst will be mixed within the electrolyte. And then you'll have a ring, which is basically platinum ring, where your reduced products get oxidized back. We can do RRDE in two different ways. So the first one, we can scan the potential of the disk and hold the ring at a particular potential. This is used basically if you want to identify by scanning the disk at different potentials, like what products are formed at each potential. And the second way is holding the disk potential at a particular potential and then scanning the ring potential. In the second way, when you hold it at a particular potential on the disk, you can ensure that a particular product is what produced when CO2 is reduced. And then you can quantify the amount of product generated on the disk by oxidizing it back at the ring electrode by scanning the potential through a potential window. So in this paper, the electrochemical studies were done using a 3 electrode system. So basically in the working electrode, you have a disk and a ring electrode. And the reference electrode is an RHE with a pH of 9.2. And then the counter electrode is a high surface area platinum mesh. And before they did any experiment, you need to saturate your electrolyte, which is sodium bicarbonate, 0.1 molar. So they did the saturation of CO2 by purging it for at least 40 minutes. And that way, finally the pH, initially the pH of the bicarbonate was around 8.3, and after that the pH was around 6.8. And then, so in this experiment, they did all the electrochemical experiments by using the second one we saw on the last slide, by holding the disk at a particular potential and scanning the ring through a potential window. And they also did some electrochemical cleanings on the disk by using CV for at least 50 cycles in the potential window of 0 to 1.8 volts. And for tin-based electrode, they did the cleaning using bicarbonate, not on perchloric acid, because it can dissolve in perchloric acid. So then for the molecular catalyst, they used nickel cyclam chlorine. So this was dissolved into the electrolyte to give a concentration of 1 millimolar. So first, let's focus on hydrogen formation on platinum. As you look at the CV here, and the platinum or platinum disk or platinum ring electrode assembly is basically it can do hydrogen evolution compared to CO2 electroreduction. So they wanted to test the hydrogen evolution on the platinum surface. So basically, they did a blank curve without holding the disk at any potential and just recording the ring CV at a narrow potential range of 1.2 to 0.05. And then they did hold the disk at a potential ranging from 0 to minus 0.4 volts. So this way, you can have hydrogen being generated on the disk, which is being detected on the ring electrode. As we see, once we increase the holding potential, the current density increases, and that tells us that as we apply a more negative potential, there's more hydrogen being generated and it's getting detected on the ring electrode. So, and then what is the Faraday efficiency of this hydrogen generation and detection? So for that, they basically subtracted the ring CVs. What you see here is just the positive CV. So they subtracted this with the blank to obtain a ring current, which is relatively constant. And they did this only in the double layer potential region where you don't have any contribution from other reactions. And then they calculated the generation current on the disk electrode. And then based on that, you can calculate the Faraday efficiency by dividing the hydrogen detection current by the generation current into N, which is N is basically called collection efficiency. And so this tells us what is the percentage of product that can be formed can be detected on the ring. So this changes with different electrodes. So you need to do this experiment beforehand, and this could be done by using like 10 millimolar potassium ferrocyanide, and then you can establish this collection efficiency. And for this work, they established that N being 0.26, which is 26% of the products collected at the disk can be oxidized back at the ring. So when they calculated the Faraday efficiency, what they found out was it is between 91 to 99%, and this Faraday efficiency was comparable to the conventional GC measurement system. Second one is carbon CO formation on AU. So this is selective to carbon monoxide, and what you can see here is AU like a disk and the platinum ring RRDE was used to evaluate the CO formation. And on this, so the potential, initially you saw the reduction potential at the disk was between -0 to -0.4. And for here, the disk potential was changed. It was initially started applying from 0 to -0.55 volts. But what you found out was that any voltage higher than -0.3 volts, it resembled like a blank CV. So those were not included in this result. And as you can see here, once the disk potential keeps increasing, there is an increase in the CO current, and it initially starts at a disk potential of -0.45 volt. And then you get a current density of about 0.35 milliampere per centimeter square at a potential of about 0.88 volts. And as you can see here on this hydrogen adsorption region, which is zoomed in this region, what you notice here is once there is a very high negative potential applied on the disk region, there is a competitiveness between the hydrogen getting adsorbed and carbon monoxide getting adsorbed. And as you can see, that there is a clear suppression in the product oxidation peak. That indicates that there is a high competence between these two reactions. And so how to quantify the carbon monoxide formation? So on gold surface. So this could be done. So for this, you need to set up a calibration curve. So for these, they set a calibration curve by comparing the measured carbon monoxide oxidation just on the ring by switching off the disk. So you basically don't apply any potential on the disk surface, but you just use the ring, like you just purge a known concentration of CO into the solution and you do a CV. So in this way, what they found out was when they increase the concentration, there is a shift in the peak potential towards positive, and there is also an increase in the current density. And this way, and they found out that if they plot this calibration curve in terms of peak current and peak potential versus the solution concentration of CO, what they found out was this increase in peak current and also the shift in peak potential was linear functions of the CO concentration, which indicates that you can either use the peak current or the peak potential to calculate your concentration of CO. So they did this by verifying, they did this verification by using the ring current or peak potential that you calculated in the previous curve. And then what they found out was indeed the CO concentration was almost same if you use either I peak or E peak. So next is using concurrent formation of hydrogen and formate ion on SN. So this they did using a SN disk and a platinum ring assembly. And for this, they applied a constant potential ranging from 0 to -0.9 volts. And what they found out was between 0 to -0.6 volts, there was only hydrogen detected on the platinum ring. And the reaction of formate producing starts only above -0.6 volts. And as you can see here, as they increase the potential, the oxidation current increases, generating more formate on the disk. And to set up a calibration curve, what they did was they mixed a known concentration of any salt of formate within your solution, and they did a CV just on the ring to see how the current looks. And what they found out was, unlike what you saw on the carbon monoxide, where it kept increasing, and here it is proportional. The current increase in the current is proportional, and also the peak current was obtained at a particular potential of 0.82 volts. So, and for this to generate a calibration curve, to examine the linearity, even with a very low concentration of formate ion, what they did was, instead of plotting just peak current versus concentration, they did the inverse of peak current versus the inverse of concentration. The other thing you can notice here is that it's not only just when you have a electroreduction on SN surface, you just not have only formate ion, and you also have formation of hydrogen because the potential is very competitive. So to identify this, they did a CV just on the pure HCOO, and then also mixed it with hydrogen. And what they found out was, when they mix hydrogen, that the peak potential of the formic acid oxidation just was like at the same potential, but whereas there is an increase in the current density in the second peak. And then, they did the Faraday efficiency, they did the calculation using the calibration curve that they obtained in the previous slide. And what they found out was, initially, around 0 to minus 0.6 volts, hydrogen was the only product that was produced. And you can also see, since the around 0 to minus 0.5 volts, the hydrogen produced was very low. So there is a very uncertainty in the hydrogen concentration that is calculated. And at a potential between minus 0.55 and minus 0.6 volts, you can see the change in was detectable. And you can see the Faraday efficiency remained almost higher than 90%. And once the potential is more negative than minus 0.6 volts, you can see the concentration of the formate ion gradually increases, and also the hydrogen concentration decreases. So this indicates that there is a change in the production of hydrogen from the reduction of CO2 to formate production. So then they used the RRDE technique and compared it with the NMR technique. And so they used inner Helmholtz plane and outer Helmholtz plane, and they used the radius of the CO atom and then the formate ion to calculate the bulk concentration. And when you have a bulk concentration of 3.37 micromolar, that corresponds that you can detect even at a very low of 4.08 in 10 to the power minus 17 mole of CO can be detected. The same with formate. So this was at last the results that they did. They changed the detection limit, electrolysis time, and also the disk current, and then saw how it changes. And what they found out was, to match the detection limit of RRDE with NMR, you need to either increase your electrolysis time by 6 times, or you need to decrease the volume by 6 times, or you need to increase the catalyst surface by 6-fold. So in this way, you can match the detection limit of RRDE, because RRDE, you can do the detection propagation in less than 1 minute, irrespective of your time, volume, or else the catalyst surface area. Next is the concurrent formation of hydrogen and carbon monoxide on the molecular catalyst nickel calcam chlorine. So initially you see on the electrolyte, just with the sodium bicarbonate, you do not see any peak, you just see hydrogen adsorption and desorption that is on the platinum surface. And once you add the nickel cyclam, what you found was that like you see a severe depression, like suppression in the platinum ring voltammogram. And this, they relate this because this could be due to the chlorine adsorption on the ring surface. But when they applied a constant potential of minus 1.16 volts at the disk, what they found was there is a sudden peak appearance, and this peak could be correspondent to the production of CO by nickel cyclam that was reducing CO2. And so they did the series of CV, and what you see here is just the positive, and then at a potential ranging from 0 to minus 1.36, but any potential higher than minus 0.76 volts, there is no reaction or production of CO. And as you can see here, that once you increase the potential, the peak potential increases and also the current density increases. But after minus 1.6 volts, you see the peak potential starts to shift in the other direction. And they attribute that this could be due to a shift in the local pH of the solution. And also with the potential of minus 1.31 and 1.36 volts, you see a secondary peak that comes in the reverse direction when you change the potential. And this peak is actually at the same potential. It's not shifting when you change the disk potential, and the current density increases, but the peak remains at the same potential. So they assume that this could be due to the like a co-electro oxidation on leaving some intermediates because of hydrogen and carbon monoxide. So to evaluate their hypothesis, what they did was they did not have any molecular catalyst in their electrolyte, and they just purged carbon monoxide into the solution. And they found a CO oxidation peak, and there is no secondary peak. When they mixed it with hydrogen, what they found was there is a secondary peak that contributes. So this kind of so this is still a hypothesis that this peak could be due to the oxidation of any intermediate species that could be formed during the electrooxidation of hydrogen and CO on the platinum ring surface. And further, they also did the like the secondary peak to confirm that they know at minus 1.16 volts you have just carbon monoxide formation. And when they just did the hydrogen bubbling into the solution, and what they found out was there is a secondary peak that's formed. So this again like let them confirm that this could be due to the co-electrooxidation intermediates produced. And the same way they established the calibrations curve, and what they found out was they plotted this disk current versus disk potential and also the product concentration. And here it's a product could be starting from pure hydrogen or pure carbon monoxide and a mix of both. And so they split, so this is a linear sepultometry you see in a different potential region. And what you found out was in the region 1, between 0 to minus 0.7 volts, there is no reaction. And in the region 2, you just between minus 0.7 to minus 1.16, you have CO is the only product. And as you increase the potential, there is an increase in the CO electrolysis current. And in the region 3, you have like both competitiveness between hydrogen evolution and also CO2 electroreduction. And also, as you can see, once you go below minus 1.2 volts, what you see is the CO2 electroreduction product gets decreased, as you can see from the product concentration. And this could be because either the molecular catalyst is getting decomposed, or your hydrogen evolution reaction activity is higher than your CO2 electroreduction activity. And so this could be also taken, instead of just doing this on just 3 heterogeneous catalysts and 1 homogeneous catalyst and just using it for only formate or carbon monoxide, they want to extend their work focusing on like complex reduction products where you have a mixture of methanol with formate or methanol with carbon monoxide. So this could also be done using rotating ring disk electrode, because when you have a co-electro-oxidation of like a complex product mixture, each of the component in your product mixture will have a significant electrochemical features that you can look around in the CV. And this features can help you to identify either the component directly or like their secondary reaction that can be produced from the oxidation of that particular product. So for example, if you look at the CV here, in the blue region, the formate always have a broad oxidation peak in this blue region. And that helps you to identify, okay, there's a formate in your product mixture. Whereas if you have methanol, methanol has a significant characteristic where you have like an oxidation peak even in the positive direction. Also, when you reverse the potential direction, you still have an oxidation peak. So that helps you to identify that there is methanol in your product mixture. And this is different from your CO oxidation peak, which has only a single peak, and you don't have any peak in the reverse direction. So in summary, they could use RRDE for fast and reliable quantification of different CO2 electrochemical reduction products. And they were able to have a calibration system established for both heterogeneous and homogeneous electrocatalysts, which they have selected 4 of them. And compared with the conventional methods, using RRDE, you can significantly have a shortened time delay between your product generation and detection, and you can also have a rapid analysis. And as you can see here, it just took them like 1 minute to complete a CV for like 3 cycles at a rotation rate of 1600 RPM. And also, in addition, then the surface product is detected by the ring because before it gets diffused into the bulk electrolyte. So it is very advantageous to detect like any trace amount of products that is produced due to a low production efficiency or during the onset potential where the production efficiency is relatively low. And also when you have a mixture of different products, you can use the unique fingerprints that is established in the CV signal by different products, and with the proper help from your calibration, and that could help you to deconvolute the peak futures, and which eventually leads you to identify which product could be present in the mixture. And with that, I would like to tell you that for next week science review, Dr. Shok would be giving the talk on rate-dependent aging resulting from fast charging of lithium cells. So with that, we can start discussing. Thank you.
Great. Thank you, Ayyappan. That was excellent. Very well done. Let's maybe we can stop sharing and come on.
Yeah.
Great. Excellent. So thoughts, comments, discussion points? Who wants to go first?
I'll go first.
Okay.
Yeah, it was a very nice presentation, and I could directly relate it to my own research right now, because what I'm working on is like the opposite of what he was discussing, like oxidizing methanol to carbon dioxide. So like basically right now in the methanol oxidation field, like there is a lot of controversies. Like there are 2 different peaks in the CV curve, like the forward scan and the backward scan. So many say that the backward scan is the oxidation of the product which is formed in the forward scan, but it's not true. But it's the methanol that's being oxidized in the backward scan as well. So I think this will be a very nice technique that we could use to actually prove that, because like there are several in situ techniques they have been using to prove those things. So I think this is a very nice technique, and I have never thought of this, and it's very useful now.
Great. Yeah. So you can present in one of these upcoming sessions after you complete that.
Yeah, exactly. Yeah, I can do that. I can try that, because with Ayyappan's last paper, which we published, we kind of explained this mechanism, like the backward scan was due to the methanol oxidation. I can do this, and we can discuss that
after the publication, of course. Yeah.
Yeah.
The one advantage of using RRDE is like you can rapidly evaluate the product, but being said that you need to have a proper calibration system that you can relate back.
Yeah.
You have to set with like actual.
For quantification, we might need a calibration study. Yes, exactly.
So,
but one challenge will be like if I'm using an electrolyte with methanol, and if there is an overlap between the methanol peaks, that would be a challenge. Then I may have to think about what can be done for that.
Yeah. Other comments?
It was really an interesting presentation. Thanks very much for the details. I was just wondering, in the application point of view, is there any applications that you can think of, or did these people continue with any of them?
What did you ask? I missed your last part.
So this rotating ring disk electrode, they found a good discovery, right? So if we are able to look at the elements and then the reactions at a very detailed level using the rotating ring disk electrode. So were they able to implement this in any of the applications worldwide?
No, actually they mentioned it because this is a recent paper published in 2020 in April. So they mentioned that they're going to extend it by evaluating this on a copper electrocatalyst. So as I mentioned that copper, you can have a mixed products starting from CO to alcohols to hydrocarbons. And that has a selective from C1 to C3 building blocks. So they kind of mentioned that they could extend their work to do an analysis on mixed products that could be generated. And the last slide was just an example how they can identify these mixed products because of their individual electrochemical fingerprints that they can identify on the CV.
So it was an excellent presentation. In slide 12, there is a change in slope, right? When they increase the potential.
Yes.
Yes. So is there any reason for that? Did they mention anything on that?
No. I would like attribute it to like the high format that is producing. Like the generation of format is more on the disk, right? So when you have more format generation, so that you can have more format getting detected, so that eventually going to increase your slope. But it's more linear if I look at that.
Yeah. So it looks like there are two different mechanisms happening at two different range of potentials.
Yes, because on the surface you have both H2 and HCOO minus. So then they do the calibration to kind of separate with which potential you have hydrogen generation and which potential you have format generation.
Also, when a new catalyst is explored and it produces a mixture of compounds. So I guess with this technique, also including the in situ techniques would reliably make this as a fingerprint technique rather than adding the expected intermediates. Using in situ technique coupled with this RRDE, they would be able to relate the actual intermediate that is being formed rather than doing a separate experiment with adding the expected moieties.
Yeah, that's true. So when they use a new electrocatalyst, so you need to do the RRD experiment in the other way. You want to probably hold the ring at a particular potential and scan the disk at a narrow potential window. So now you can see how the product gets formed and how the initial CV on the disk looks. And based on that, okay, so if you're interested in methanol formation, then hold it at that potential range to get detected in the ring. And then, as you said, just using in situ FTIR or any X-ray technique to further quantitatively like verify what they got is indeed there is no like intermediates mixed or what is the concentration of the product that's being generated.
Yeah, identifying the intermediates, it would be easier if those in situ techniques can be coupled with this together.
So just a quick question. Did it try XRD to find the structure of the generated compound?
No. So their major point of like this work is like we want to do a rapid analysis, like less than 1 minute. We wanted to see what product is formed. Right? So that's why if you look, they didn't do CV, like only the cleaning CV cycles were done for 50 cycles. But after that, when they did the product evaluation, it was just 3 cycles with like 100 millivolts per second. So they can do it less than 1 minute. So.
Okay.
Yeah, I felt the study was very well done, very well controlled. And to your point on the in situ or in situ techniques, I think the whole point that they were trying to go after is without those, how can you detect? And you need the 6-fold increase in volume or the surface area. So I felt that their way of doing control studies was brilliant. I was going through the data and paper. I will have a question, and then the second paragraph, they will have the answer. So it was very well done. So in terms of the peaks that are appearing, for example, at negative 0.55 in CO, there was a shoulder peak. And so subsequently, they went in and then analyzed all the different regions and then the mixtures. So I thought it was very well done, and it can be extended for rapid screening of catalysts. I think that's Amazing. So very well done paper. I think very comprehensive, and control studies were good. That was my feeling reading this paper.
Yeah, and also they also did like when you have like both hydrogen and carbon monoxide production. So they saw like around after minus 1.16 volts, there is a negative shift in the peak, which was contrary to the positive shift. And they also did some pH study, which is attached to their another paper. So I have to go through that to identify. So it was like, as you said, a well-studied paper. Yeah.
Yeah. So one region that they could have spent a little bit more is, I think, the hydrogen oxidation peak region. In some of the reactions, there were some peaks where you expect no peaks at all. They didn't go into the details there. So that's more as from a critical viewpoint of view. That's what I saw. Okay. If there are no further comments, next week, as Ayyappan mentioned, we'll be going through rate-dependent aging resulting from fast charging of lithium-ion cells. And if any of you would like to participate and lead the discussion, please send an email to info@vetrilabs.com. Thank you for joining us. See you next week.